All right. So a chemical reaction rate, or the rate of a reaction, is the change in the amount of a reactant or product per unit time or over time. So we can write the rate of a reaction with respect to the reactant or to the amount of product. So our rate with respect to the reactant is the change of our concentration of reactant over the change in time. And there should actually be a negative out here. You'll see in the next example, in an example. And let's talk about it now, though. So the reason that it should be a negative here is because our reactants are being consumed. So if we're writing the rate with respect to the amount of reactant, over time we have less and less reactant, right? This is our expression if we write the rate with respect to product. This is the change in product concentration over the change in time. So the amount of our reactant or product is expressed as concentration. It's expressed as concentration. And how we are writing the rate with respect to reactants or products is called a rate expression. This is a rate expression. So let's look at an example of writing a rate expression. So we have this chemical reaction here. And we're going to write the rate expression with respect to the reactant and to the two products that are formed. So N2O5 is being decomposed. So it's written, the rate is negative because it's decomposing, it's being consumed, negative of the concentration of N2O5 at some time point 2 minus the concentration of N2O5 at our initial time point 1. And that's over the difference in time, time point 2 minus time point 1. For our NO2 or O2, our product formations, these rate expressions, right, we have a positive value out here, and it is the change in those concentrations over at those specific two time points, which we've just written as T2 and T1, over the change in time. So the main thing to remember here is we can write our rate expression with respect to our reactants or to our products, and they are the change in concentration of rates of reactants or products over the change in time. So let's look at how we would calculate our reaction rates. So here is a reaction of hydrogen peroxide that's being decomposed. Over the course of a day, they measured the concentration of hydrogen peroxide every 6 hours. Every 6 hours, and that's what's shown here. And from this, they calculated these rates of decomposition at every time point. So here is the difference between any two time points, the difference in the hydrogen peroxide concentration, which is shown as delta H2O2 concentration. So let's do an example of how we would calculate it, of how we would calculate our reaction rates. So remember, our rate expression with respect to hydrogen peroxide decomposition or our reactants, amount of reactants, is going to be negative the change in concentration of our reactant, which is hydrogen peroxide, over the course of some time, over the change in time. So if we calculate the rate in the first 6 hours, we see that at 6 hours, the amount of hydrogen peroxide was 0.5 molarity. That's what we have here, minus 1 molarity, which is what what's the concentration that we initially started with of hydrogen peroxide at time point 0. In our denominator, we just do the difference in time, which is 6 hours minus 0 hours, and we get 0.0833 molarity, right, which is moles per liter per hour. And that's what they have here. That's what they have shown here. If we calculate it in the last 6 hours, right, where our final time point is 24 hours and our initial time point over the last 6 hours is 18 hours, the rate is 0.010 molarity per hour. So what we see here is that as hydrogen peroxide is consumed, or as it decomposes, the concentration decreases and the rate slows down. The rate also decreases, which might intuitively make sense, right? As more hydrogen peroxide is used up, is decomposed, our rate slows down with a decrease in concentration.